Hello everybody, we're back and today we're going to be talking about concavity and points of inflection. Before we begin, I'm going to have to introduce a new concept to you, and that concept is taking the second derivative. So let's start with our do now. If f of x equals x cubed plus 2x squared minus x plus 1, you all know what this notation means. F prime of x means find the derivative. So the derivative of this function would be 3x squared plus 4x minus 1. Now, if you move down to part B, it says find f. This is double prime. When you see two tick marks, that's double prime, and that means the second derivative. But that's a pretty easy concept. If I'm taking the second derivative, that just means I'm taking the derivative of the derivative. It makes perfect sense. So now we're going to start at our derivative function, take the derivative of that, and you get 6x plus 4. So there's our function, there's our first derivative, and here is our second derivative. We're pretty much going to be focusing on our second derivative today and what it can tell us about the shape of a curve. Yesterday we studied how we can use the first derivative to help us determine where a function is increasing or decreasing, and whether or not it has any relative maximum or minimum values. Today we're going to talk about how the second derivative can help us determine intervals of what we call concavity. Okay, so now that's going to be a pretty tricky concept, so I'm going to take a few minutes to describe it. A curve can increase and decrease in different ways, right? Our curve can kind of go up like that. Our curve can bend up that way. That would be increasing. Our curve can decrease like that, or our curve can decrease like that. And I'm sure you can kind of visualize this, just by looking at, thinking about the graph of a function. Our curves can also do this. Now these are linear functions, right? These have no bend to them. Today we're going to be discussing bend, so we're not going to really be talking about these, so to speak, today. We're going to kind of X them out of the picture for the time being. So let's talk about how we can use derivatives, or how we can use the second derivative to help us. Well, we know f prime represents the rate of change of f, right? And we know when f prime is positive, that tells us f is increasing. And when f prime is negative, that tells us our function is decreasing. So with this in mind, let's think about what this can help us with. Well, if f double prime, or if the second derivative is positive, that means f prime is increasing. It's kind of hard to think about in your head, but we'll get there. And this also means when f double prime is negative, f prime is decreasing. Still, I know that seems a little bit confusing to you, so let's just take a few more steps in this process. All right, so we said the second derivative is going to help us with this concept called concavity. And all concavity is the shape of the curve, or what I want to call, or what I like to call, the curvature. Okay. Or the way the curve increases or decreases. So if we take a look at these two functions here, we have f of x. If I take and I make little tangent lines along this curve at just random points, if I draw the slope of the tangent line, right, if I make little tangent, what would you say if we had to put a number to this? Could I call that -4? That means f prime is -4. The slope of this tangent line, let's say that's -2. This slope would be 0. This slope would be 2. And this slope would be 4. Okay. So if I move from left to right, what can you say about f prime? It goes from -4 to -2, 0, 2, 4. What's happening with those numbers? They're getting bigger. So in this case, f prime is increasing. Okay. When f prime is increasing, we call that curvature concave up. Now, you don't have to do this in an example. You don't have to draw tick marks. That's not what this is about. We just have to notice the connection. If f prime is increasing, right? When does f prime increase? When f double prime is greater than 0, or when f double prime is positive. So when f double prime is positive, that means my curve is going to be concave up. If we look at this shape over here, again, the curvature, if I was to draw little tick marks or mini slopes along this curve and give these slopes number values, what do you say about the numbers here? 4, 2, 0, 2, oh, -2, -4. Okay. We could say these values, or the values of f prime, are decreasing as we travel around a curve with this shape. Okay. When this happens, the shape of the curve is known as concave down. When does f prime, what is the concavity when f prime decreases? I'm sorry, what is the second derivative? I apologize. The second derivative is negative when f prime is decreasing, and that's going to make the shape of our curve concave down. Now, just like direction, anytime the concavity of a curve changes, we're going to have a special point. And with concavity, these are going to be called points of inflection. So let's talk about some of the steps we're going to take when we're working through an example. Okay. Basically, it's going to be the same as the first derivative test. The second derivative does not really have a special name. It's just like test for concavity. Concave up, concave down, inflection point. Okay, we're going to find our test numbers just like we did yesterday by setting it equal to 0 or being when it's undefined, but defined in the original. And again, that's something we'll come up with when we get to those types of examples. We're going to put those numbers on a number line. We're going to test our intervals, and then we're going to describe our intervals as concave up or concave down. And then if we have any points of inflection, we're going to describe those as well. And you'll see what I mean when we move through an example. Now, to help you remember, we have a little saying. And that saying is, moving on. Let's look at a few examples now. So now for each function, we just want to determine the intervals of concavity and identify any points of inflection. Okay, if you notice, I took the function from above, so we pretty much already have the second derivative, but it's easy enough to find. Okay, so remember, I'm looking for second derivative, so I'm looking to identify concavity, so I will be using the second derivative. First step, I want to set my second derivative, 2 tick marks here. I want to set my second derivative equal to 0. And when I do that, I get x equals -4/6 or -2/3. Now, we're not looking for increasing or decreasing. We're looking for second derivative values. So we're going to evaluate, we're going to set up our number line, and we're going to label it with the second derivative. I'm going to put my test number. Notice it's not a critical value, so to speak. I call it a test number. And I take a number a little bit less than. So if I'm a number less than -2/3, I could take a number like -1, -2, -3, just something in this number, in this interval, and plug it into this derivative. And let's say I plug in -1. I would get -6 plus 4, which is a negative value, So the second derivative is negative here, which means my function is concave up, like a cup. If I go in this interval, pick a number here, 0, 1, 2, whatever. If I take 0 and plug it in, I'm going to get a positive value here. Oh, what a mistake. Concave down like a frown. I feel like I'm in the classroom right now. This section is up, concave up like a cup. Now, if we want to describe our intervals of concavity, we could say our function is concave up from negative 2/3 to infinity. I haven't mentioned this, but we can also use set notation. Either way. And concave down. Well, where is it concave down? It's going to be over here. Negative infinity to negative 2/3. Or x is less than or equal to negative 2/3. Now, I prefer to use interval notation at this point, but it's really, we can bounce back and forth. It's no big deal. Now, if we look, we want to also notice in the graph that there is a place here where the second derivative is 0 and I change concavity. So this is going to be at x equals negative 2/3. We're going to have a point of inflection. And to find the actual point itself, if you're asked to find the actual point on the curve, you're going to take negative 2/3 and plug it in to the original function. And the y value when we do that is 61 over 27. So our point of inflection would be negative 2/3 and 61 over 27. That's our x, that's our y. Now be real careful with these questions because sometimes they only ask you for the x value, and that's okay. I just wanted to try to work through one question, showing you all the different steps. Now, let's take a look at a different type of function. Okay, that's a polynomial, and now let's look at a rational function. Okay, so we know there's a little bit more work involved with these. Again, I'm going to start with, let me find the derivative. Now, like I've told you from the very beginning, when we're looking to find the derivative, what makes the most sense? Should I do the quotient rule? Okay. Should I do the chain rule? Now here's a perfect example. Since I do not have a variable on the top, I can just bring this up and do the chain rule. It makes life so much easier. My first derivative is the derivative of the outside, subtract 1, times the derivative of the inside. So the first derivative, if I simplify this, is just going to be negative x plus 2 to the negative 2. Now, why didn't I write that with positive power? Because I know I'm not dealing with the first derivative. I'm talking about concavity. So I need to find the second derivative. So the second derivative becomes negative 2 times negative 1, 2, derivative of the outside, times the derivative of the inside. My second derivative is 2x plus 2 to the negative 3rd power. However, since I know I'm going to be doing some work with this, I want to rewrite it with a positive exponent. Now, since my second derivative is a rational function, I need to look for where it's 0. I need to look for where it's undefined. Numerator equal to 0, that's never going to happen. Denominator equal to 0. Some of you can see this in your head, that's fine, but if you have to solve it, raise each side to the reciprocal power. X plus 2 equals 0, so it's going to be defined when x equals -2. But if we look at this and we plug it back into the original, it's undefined in the original. So remember, technically, this is not a test number, but we still have to test it. It just can't be a point. Okay, we're still going to put it on our number line, and we're going to use this number to help us determine what's going on. I'm going to go back up. I'm going to make my number line for the second derivative. Notice, I pick the nice function here because it's easy to evaluate. Second derivative, -2. Pick a number less than -2. What's happening? When I have a number less than -2, my numerator is always going to be positive, and my denominator is going to be negative. So this interval is negative, which means my function is concave down. If I pick a number bigger than -2, my numerator is always going to be a positive value. My denominator, let's say I use 1, cube a positive, get a positive. And your graph is going to be concave up. Okay. Now remember, this was not technically a point on the curve. The graph is going to be concave up from -2 to infinity. The graph is going to be concave down from -infinity to -2. Okay. Now this curve will not have a point of inflection. Let's take 1 second right now and talk about why not. Okay. Basically, it looks like it should. It goes from negative to a positive on my curve, but if you remember, -2 is undefined. So there's no point there. This is where you really have to kind of remember your behavior of functions. At -2, since this is a rational function, basically there's some sort of asymptote in the curve there. Okay, and if you're confused and if you want to try to make sense of this graphically, there's no harm in plugging things in your calculator and looking and seeing the picture and trying to make connections between the math you're doing algebraically and what you're going to be seeing graphically. -2, the graph is concave down, the graph is concave up. Once again, there is no, even though my graph changes concavity, there is no point of inflection for this curve. Tomorrow, we're going to actually put all these concepts together, and we're going to graph by hand. But today, I would just like you to go work on your homework and practice some of the examples that I have there. Thank you. Goodbye.